However, I do want to mention, I want to make sure you understand that Cube can easily integrate with any macro model of socioeconomic change. And so here's an example of a multi-scale model system where we have CubeLand is the green box here, integrating with a macro model providing control totals that go into the process, as well as a micro model, let's say from a scenario planning or a community visioning process in which people go out and generate different land use patterns. And that real estate scenario might be based upon this sort of visioning exercise involving community input, and then it goes into CubeLand as sort of a base land use assumption or perhaps a policy scenario that then might have different interpretations in terms of market effects, how the market will respond to that land use. And CubeLand goes in and does its iterative feedback thing with the travel model, where CubeLand provides zonal data, households, and firm location to the travel model. The travel model runs its process, comes up with congested travel costs. Those become accessibility, and we go round and round until we hit this equilibrium that I showed you earlier. And so the idea is we can integrate with these macro and micro models rather easily, and then that creates a tool that really has some nice properties in terms of covering all the bases in land use and transportation planning. And here's just another example. Again, we're using the macro model in a very similar way, to forecast the control totals for CubeLand. And maybe we have some sort of base land use assumption for the base year, but then as we move into forecasting mode, CubeLand, of course, comes up with different land use projections in the future. These are output by CubeLand at the zonal level, whatever your zones might be, and these could be very fine. They could be down to parcels, or they might actually be, transportation analysis zones in which you might want to use a micro model, a GIS-based model, to disaggregate those zonal outputs for display and presentation to the public or land use planners or other colleagues in GIS. So the fact that this is all inside a GIS environment makes it very easy to do these integration processes. So, that's sort of, one vision for how we could use CubeLand in coexistence with these other types of models. However, I also want to address, when it's inappropriate to use a rule-based or simulation-based model, and when we think it's an especially good opportunity to use CubeLand. And you see the two targets we have here on the right-hand side. The top one represents sort of the definition, the textbook definition of low precision, and the bottom one is low accuracy. So we have a cluster of dots, each represents like a forecast. And if every time you run the model you get a slightly different result, and they're all kind of around the bullseye but not right on the bullseye, that's a situation where you have low precision. Whereas on the bottom side there, if you have a bunch of forecasts that are all close to each other but all kind of off the mark, that's low accuracy. And basically, the question here is simulation-based models that don't compute in equilibrium like CubeLand does are questionable as regards their precision because they're inherently random, and every single time you get a forecast, it might be just a little bit different or maybe even a lot different from the last time you ran the model without changing any of the input parameters. And that's just the nature of stochastic processes used in simulation. Rule-based models, on the other hand, are all sort of subject to the biases we plug into them. It's very much a garbage in, garbage out situation, and basically you just plug in your assumptions about how land use development and location occurs, and you get out what you put in. So, it comes down to the accuracy of the modeler and the person running the model, and that's a very subjective and contentious thing at times. So those are questionable in terms of their accuracy. And therefore, these kind of rule-based and simulation models might be inappropriate when you really need to do scenario comparisons of build and no build, like I showed you in Cube, or when you really need economic measures like rents, for example, coming out of a market-based process that has a lot of economic behavior built into it that's very sound. And CubeLand is really uniquely capable in this regard. It's uniquely capable of efficiently computing a spatial real estate market equilibrium for multiple firm and household types. This is really needed in order to make stable scenario comparisons of economic benefit costs and other measures, especially when you're looking at, key bono, who benefits from a policy, which household types benefit most, which firms are going to be impacted the most by our land use and transportation policies. CubeLand can actually speak to those issues and answer those questions, whereas a lot of non-economic models really just can't. And so that's a special consideration to keep in mind, depending upon what you want to use the land use model for. This issue of accuracy and precision also has implications that are just sort of practical implications for model development, and regardless of whether you need to answer those kinds of scenario comparison issues, it can also be a lot more costly to develop a model that's not accurate or not very precise. And this is maybe a contributing factor to the historical difficulty in calibration of these simulation-based land use models. If a model is at least precise, like cubeland is, because it computes this unique equilibrium, then you know which adjustments need to be made to improve the accuracy of the model in order to get closer to that bullseye. If we have a situation like the bottom here, where we have an equilibrium, the dots are all close to each other, we're getting basically the same result every time we run the model. But let's say we're not calibrated yet, so we're not close to the bullseye. We at least know which direction to move. We know where the bullseye is, and we know how to get there from here. And that's a big difference between this kind of model and a model that's sort of random, and we have a lot more spread in between individual runs of the model, and it's difficult to calibrate for that reason. In addition, cubeland's parameters can truly be estimated statistically from empirical data. You can really use observed land use choices and land use distribution patterns to estimate the parameters of cubeland. And I make a distinction here between statistical estimation and calibration, where calibration just means heuristically or trial by error adjustment of all the model parameters and inputs until you achieve a scenario that matches what you observe. In effect, with a simulation-based model, that means you're chasing around a moving target at times, it feels like, because you don't know where you are, which direction to move, or how to get there from here. Whereas with cubeland, you actually estimate the parameters from observed data, and that gives you a lot more confidence, I think, in the robustness and the rigorous quality of the model you're using to forecast your results. One last comment on comparisons of different types of models. All of these kind of fit into an overall path that most agencies are following in getting to the sort of, quote-unquote ideal or perfect model. Which, you may disagree with this. Maybe it's not an activity-based model. Maybe it's not simulation-based. But we certainly see a lot of agencies moving in that direction. So this is kind of a description of the general trajectory we've seen. And this isn't a Siegel Labs observation. This is taken straight from a paper by Wegner in 2004, adapted from another paper in 1998 by Miller. And the idea here is that transportation and land use model development go hand in hand. If where we want to get to this bottom right-hand corner where we have activity-based land use models and activity-based travel models, we still have to go through the process of getting to a logit-based or market-based model like cubeland for this very reason I mentioned on the previous slide, because it's so much easier to calibrate a model in that form than it is to go straight to the disaggregate form of that model and calibrate it. And this is sort of a driving concern here, skipping over that step might lead to a much more difficult experience implementing a model. Basically, the key difference between these two things in some cases with some simulation-based models is only whether you're applying the model to individuals or to aggregate quantities. But basically, it's sort of like if you want to get there from here, this is the way to go. And so if you're in a situation where you've sort of had some experience with sketch planning or scenario planning or GIS-based or rule-based models, or you've done some activity and judgment or qualitative-based forecasting, and you're ready to move forward, cubeland falls into that sort of logical next step family of models for an agency or an organization like that. Now I'd just like to talk a little bit about new features in cubeland, and then we'll move on to our case studies. In 5.1, of course, we have enhanced our integration with ArcGIS, which has been there since version 4.2 actually, made official in 5.0. Inputs can be stored in attribute tables of polygon GIS layers in an Esri geodatabase, and we now support enterprise geodatabases as well as file and personal geodatabase types. What enterprise means in practical terms is you get access to a much more professional quality, intense, fast, efficient database platforms like Oracle and Microsoft SQL Server, rather than just a Microsoft Access file sitting on your local disk. In general, in terms of the geographic resolution, again, it's scalable. Zones are of arbitrary size are used. We can make these be parcels, blocks, traffic analysis zones, census tracts, zip codes, but put a check mark here next to traffic analysis zones because those are usually the level of resolution which is easiest to integrate with the travel model. And categories are used to represent variations within the population inside of these zones. So here's Also, one of the other changes in CubeLand 5.1, the biggest change is that in the previous version, we had sort of a fixed data model, like a lot of land use models do, where you have to collect certain specific attributes for your real estates, your zones, and your agents in order to run the model. And we went through a big process in 5.1 of redefining the input data model so that it's totally flexible. And basically, when people ask us about data requirements, we say, you know, there aren't requirements. Tell us what you have, and we can fit it into this data model. And I've circled here on this diagram, which is just an entity relationship diagram for the data model, the places in the real estate table, the zone table, and the agent table where you have ellipses. And what you see here, the attributes like lot size, built area, income, etc., number of persons per household, etc., are all just examples. You can put whatever data you want to use or is most meaningful to your model inside this relationship diagram and use it in your CubeLand model. So it's a very flexible framework, and we foresee a lot of interesting things happening with comparing different kinds of data models. Users can come up with their own bid function specifications using the variables that are most salient to them, and it's going to be really interesting to see as a bunch of these different models come online how their bid functions compare and what specifications are similar and different. So that segues directly into our case studies and applications. Hopefully Dr. Francisco Martinez is on the line. He could talk a little bit about Santiago. Then I'll talk about the model in Thailand, Montgomery, Alabama, Fredericksburg, Virginia, just starting up, and Kerncog as well. But our first application of this framework, of course, is MUSA in Santiago, Chile, where the modeling framework has been used to evaluate mega projects, so-called transportation facilities of a vast and region-shaping nature, like the Trans-Santiago BRT, Cerrillos Airport, Central Ring, as well as the analysis of optimal location subsidies, using real estate prices to drive household and firm location in order to minimize things like transportation costs for schools and minimize emissions, including things like carbon dioxides. And this kind of analysis is useful in permit trading. So let's see if Santiago, are you able to, oh, you're muted by organizer. Let me see if I can unmute you. Oh, he's no longer there. Make present, no. Let's make you panelists. There we go. And unmute. Francisco, can you hear me now?
Yeah, can you hear me?
Ah, perfect. Now I can hear you. I'm sorry. So there was just some technical difficulty. Thank you. Sorry for making you wait so long without being able to hear you.
Okay.